Thank you. Thank you. My president. So, on this note, I want to call on we want to start the first keynote speech for today, or keynote address. And we entitled it Professor O.A. Agbede Keynote Lecture. Professor Agbede is a renowned professor of geotechnical engineering, though late. So we'll be having this lecture in his honor. So I want to call on Professor Marwan Shaheen, the VP Africa, ISMG. You're welcome, sir. Let me bring it. Can he put it on? Help me put it on, please. Has he given you his own? So this is, if you want to hold on to the red the laser is there. It's showing. See it there. You have to hold it. Then you want to change. Press this one.
Okay. Okay. Good morning. First of all, I'd like to thank organizing committee for inviting me to be a keynote lecture here with you. Excuse me for my cold. Today, I'm going to talk about apparent earth pressure for supported deep excavations. I'm going to give a historical background, a role of field measurements, and also recent updates. Okay, I'm going to start with an introduction, giving information about earth pressure, classical types of earth pressure, apparent earth pressure, and then I'll talk about types of walls and the Greater Cairo. I'll talk about the project Greater Cairo Metro Line 4, phase number 1, instrumentation and monitoring. I'm going to talk about this. Pre-shearing effect and explanation of Jacob pressure cell reading, back calculated of apparent earth pressure, and then agreement with literature, and then I end up with some conclusions. Okay, we know that geotechnical engineering, we have necessary to a lot of opportunities to have basically retained soil behind the structures or walls. So like cantilever retaining examples, braced excavation, anchor sheet pile. The earth pressure that we have classically, we have 3 types of earth pressures. Basically, depending on the movement of the wall, if we have a wall retaining soil, then depending on the movement, the direction of movement, amount of movement, will have the earth pressure. No movement, it will have an at rest. If we have the wall, the soil pushing the wall, then we'll have an active earth pressure. On the other side, we'll have large displacement, basically the wall pushing the soil, and the soil will give a resistance, which we call it passive resistance. Basically, the passive and active, we can basically find them by using like classical theories, Coulomb and Rankine. And the at rest, we can use the Jacques equation or the or development of that. Again, this is active and passive using Rankine. You can use the K active and K passive, as you can see here, with the definition of the active, 1 minus sine phi over 1 plus sine phi, and the K passive is 1 over the K active. As for Coulomb, we use the trial wedge analysis to get trial analysis in order to obtain the column pressure, the passive earth pressure, and also active earth pressure. The at rest, we can have the Jackie's equation, and one version of this equation is 1 minus sine phi, and this is we call the K naught, or the zero pressure K naught at rest, when we have basically soil in the normally consolidated situation. If the soil is over consolidated, sand or clay, then we have this form of K naught, K0 over consolidated is equal to K0 in the normal consolidated, which is 1 minus sine phi, multiplied by the OCR to the power of 0.5. So, some literature says it's 0.5, some others says it's sine PCV, and so on. Basically, if we have a cantilever wall and then we have the soil pushing the wall, then we can get the direction of pushing the wall will have a active pressure, as we have in this side. On the other side, the wall is pushing the soil, then we'll have passive earth pressure, and it is a triangular distribution. And of course, we know that if there is no movement, then we have an at rest. If we have a braced wall in a deep excavation, then the movement pattern is different. It is not up to the theory of Rankine that we can imagine that how to calculate. Is it moving? Okay, the soil basically pushing the wall, giving movement. Then we're supposed to have an active, but this is really not an active in cantilever mode. If we have a support, the support restrains the movement at a certain place. Yes, it is restraining the movement, but it is not really actually a K naught condition. So it's a complicated situation of pattern of movement, and so we cannot use basically Rankine or Coulomb. Okay, between free cantilever and braced wall, okay, there is a difference, as I mentioned. Active, passive, at rest, no, not directly applicable. And then we have different pressure would be applicable. What would be the different pressure? Actually, this is conceptually, this is a good place to intervene with numerical and have a finite element analysis and model the problem, and then get more information about the pressures and the straining action in your structural members in the system of the support. However, in the early development, at the time of Terzaghi and Peck, when they started all the excavations in all over the world, mainly Europe and US, there was no finite element at the time readily available. So they used the Terzaghi and Peck started in the 40s and late 40s, started the approach of the apparent earth pressure. In the apparent earth pressure, basically during any excavation, we will observe or measure the forces in the support, in the strut, and then we take this pressure, we take this force divided on the area of basically significant or relevant pressure that is acting on the wall, and then basically get distribution of pressures behind the wall, and then we can have, based on that, we can judge an envelope of pressure that we can use, and basically using it will be we can use it in a simplified way in order to get the straining action of our structural members. 1969, Professor Peck put this apparent earth pressure diagram, basically based on Berlin, Chicago, New York, Oslo, Toronto. Okay, all of these, they have excavations or metro and stations. So they had all of these excavation was monitored. They monitored the pressures on the forces, not the pressures, and they get this envelopes that are used for the in the profession. Further development after that, FHWA, again, this is for sand, for the stiff, hard stiff clay, and so on. It's available. Types of walls. We have soldier piles and wood lagging. Actually, lagging, it is typically it's wood lagging, timber lagging. But in some places we can have a concrete lagging. They can put a precast blocks or precast members, and they can use it as a lagging in between the edge pile, the soldier edge pile. We can have sheet pile wall as a retaining wall. We can also have the piles basically as a contiguous pile. We have a tangent piles or even secant pile where we have when we have to have a tight system, concrete and slurry piles, and then to have an impervious wall. And then we have the diaphragm wall, reinforced concrete wall. And as you can see, we can have several thicknesses of the wall depending on the machine or the equipment that you are using to excavate. We have the 0.6 meter, 60 centimeter, to about 120 centimeter in thickness. As you can see, all over this all of these walls, okay, this is in the direction of increasing the stiffness of the wall. And even in the diaphragm wall, okay, the thickness of the wall will be basically different between 60 centimeter and 120. And even in the piles, depending on the diameter of the piles that are going to use, will have stiffness. We have to remember that most of the early measurements that we have in excavations were based on Berlin Wall. At the time, okay, it was not popular to have piles or diaphragm wall at the time of collecting the information or the measurements that they have. So at the time, it was soldier pile with wood lagging. This was the system that they collected measurements for. I'm gonna get to field case, the Greater Metro Cairo Metro Line number 4, phase 1, that has about 12 locations, 12 stations, and it's about 19 kilometers long. The the stations that we consider in this study and in this presentation was station 3 and 5, where the sand, okay, is mostly all the soil that we have is sand, and there is no groundwater, no groundwater table. Okay, this is typical cross section. It has the station will have it is a diaphragm wall with a thickness of very rigid, stiff wall, 1.2 meter. The this this is diaphragm wall, and also the raft is probably thicker than 1.2, and also the roof and also the concourse slabs, and in between those slabs are 1.2 meter thick, and these are stationary slabs. However, at a certain point, when the distances between those, there would be an intermediate temporary support, a strut. And also this information about the stations, this was basically constructed using the top-down construction. So as you can see, we have all of these points of support. And this is a plan of one station. This was the cross section, and this is the station. Now, it's very important in all the uh, uh, projects of deep excavations, and also so many other projects, but mainly the deep excavations, we usually have to have monitoring, instrumentation, and monitoring in the process. Very significant part of the budget of the project is to instrument and also monitor all the info, the points that we have here. If this is really a typical cross section showing width, depth, and supports the excavation. We have also the movement, horizontal movements, forces in support. We have pressures. We have also movement and the ground surface. We have soil. We have settlement, and so on. So all of these are information to basically to monitor. And also, if we have a structure, we have to monitor the structure that we have. Of course, like depending on if we have the structure, then we have if we observe it, we have a dilapidation survey first, and within the dilapidation survey, if we found the structure has some cracks, then we put some instruments to measure the progress of changes in the thickness or the width of the cracks. So this is also we can put also in the land, okay, extensometer to measure settlement with depth, and jack out pressure cells that I'm going to talk about. Okay, in this Geocon, okay, provided jack out pressure cell. This is a special instrument to measure the pressure behind the wall. So basically, these are the instrument, and this is the different components of the instrument. Usually, we fix it with the reinforcement cage, and we put it in a certain way that the one that we are gonna use to measure it will be facing the direction of the soil. It is very important to know that there are several stages of basically installing this instrument. For example, like we have to excavate. So the cell at the beginning is in the air, and then we excavate. We can have fill with the slurry, and then put the jack out pressure, install the jack out pressure, and then have a contact with the soil. Make sure that you push a little bit to and have a contact between the soil and the cell, and then pour concrete, and then the concrete will be curing, and then after that have to stabilize, and I'll show you how was the reading will be. If we imagine the relationship between effective horizontal stress and effective vertical stress, then these are the stages that I talked about earlier. At the beginning, we are in the air, and then we put in a slurry, and then between, for example, here, from 2 to 3, pouring concrete. As you can see, from 2 to 3, 3 is we jumped a little bit, because when the concrete is in a fresh state, it will be like not liquid, but it's not really solid. So this is how it's just pushing a large pressure. And then when it's cured, then the pressure, okay, the pushing of the cell will be a little bit restrained because of the solidification of the concrete. This actions or these stages will make sure will induce some sort of movement to the soil that I will discuss. And this is the movement pattern. Okay, from one, this is the changes in the movement, and also the changes in the horizontal stress. And as you can see, they are all at the same vertical stress because we install it at the one depth. This is at 3 in one station at 3 depths. And this is basically the changes with the horizontal movement with the pressures, okay, with time. Let's go back to 1993 with Mezri and Hayat. Maybe I'm influenced by Professor Mezri because he was my advisor, and Hayat was my office mate. So, and I helped him a lot in a lot of triaxial tests in a keynote condition. He was studying the influence of difference factors on keynote. One of the factors that he was studying in the triaxial cell, basically effect of pre-shearing. Basically, in this, basically you have a keynote condition. You impose it in the triaxial cell, and then this is when you have just a jump a little bit in the pre-consolidation pressure, and then we have a continuation of the increase in the horizontal stress with the vertical stress. But here we impose some sort of pre-shearing where we have, for example, this is pre-shearing like this, and basically how far is this point, the highest point from the keynote P line, then this is delta H, delta sigma H, IS, okay? And then you keep it for a while. In this situation, you are not restraining the cross-section area of the sample. So it's not in a keynote mode. But once you have a little bit of time and it stabilizes water pressure and so on, then what you are going to do is you are going to impose in the test, impose the keynote condition, restraining the cross-sectional area, the new cross-sectional area constant. And then either with time or with the increase in the horizontal stress, there will be a residual change in horizontal pressure on the cell or on the member that you are using. Having this in mind, and this is basically the movements in some of the stations that we have. And these are the movements. If we take this and see when it stabilizes, we can see that, okay, Mezri and Hayat had in the triaxial cells, they had delta sigma prime H equal to delta sigma prime HI divided by 2.5. Based on the data of the metro line of these two stations, we got the same equation, but with different factor, so which is close. This is laboratory, triaxial cells, and this is in the field. Now, once we passed all of these changes in the horizontal pressures in the jack-out pressure cell, with time and with the progress of excavations, and we got to changes in excavation, the last stationary excavation will be, we have the pressure that we have, and then we plotted this versus depth. And these are the raft and the roof and the anchors, and sorry, not the anchors, the slabs. So those are the values of the horizontal pressures that we measure. We divided this by sigma prime V0 in order to obtain the K, coefficient of horizontal pressure, lateral pressure, and then we normalize it by K active. So basically, K active, similar to what Peck used to do, basically 1 minus sine phi divided by 1 plus sine phi. And then K over K active that we had, as you can see, we had a trapezoidal, almost a trapezoidal shape, but we have minimum and maximum, and this is the average. Basically, Peck in sand, he had a rectangular distribution with 0.65 K active. The Federal Highway had also 0.65 K active, but it had it in a trapezoidal shape. But amazing that this is not 0.65, it's really more than 1. It's high, very high horizontal pressure. We measured very high horizontal pressure. We tried to make it a little bit easier. So maybe we can normalize it by K-note. And we have to remember that K-note in a normally consolidated way is 1 minus sine phi. However, the sand that we have here was very dense. A lot of the SPTs were like 50 and refusals and so on. So we had a very dense situation. So either very dense or an over-consolidated, dense and over-consolidated sand, which means that K-note might not be the same as the K-note of normally consolidated. So what we had is basically we decided to normalize the K divided by K0 in the normally consolidated mode. And as you can see, we had the same data, but in a different normalized way, but in a trapezoidal way, and minimum, average, and maximum. And as you can see, they are much larger values than traditionally or conventionally as measured by Peck and co-work. We try to see in the literature what's okay, are we okay, what are we doing? So basically, many authors in the literature, starting from 96, where they have their study, this is from all a numerical study, maybe at certain point they may have some measurements, then they says, okay, Peck's apparent pressure diagram is underestimated the strut loads significantly. They measured the strut loads, so they had it, Peck's underestimated the pressures. Same with Hashash and Whittle, 2002. Basically, they have smaller value by Peck's chart, and also we have a stiffness. They have a very stiff wall, and they said that, okay, probably this difference is because of the stiffness of the wall. Again, since 2010, again, underestimation of Peck, underestimation the measured apparent earth pressure. Same as in 2022, we have Hsiang et al. Again, underestimated, Peck's underestimated the applied or the measured average pressure. So apparently, we have to stop here and say, okay, we have to remember that Peck's, when he measured the pressures for all of these during the 40s and 50s and 60s, okay, the system of the wall was only a Berlin Wall, which is a flexible wall. With the developments that we have now, I think we are getting more stiffer wall, more rigid walls, okay, that we are using in the underground excavations. So this explains that it will yes, Peck's apparent pressure diagram might be useful, okay, but it is just applicable to a certain type of walls, that is flexible walls. But we need, as engineers, I know that now we are at the time of AI and we are at the time of numerical analysis and 3D, finite, very sophisticated analysis. But as engineers, I am from the school of Terzaghi and Peck, who really basically says that we need a simplified method, or we call it the back of the envelope method. Back of the envelope method means that it has a certain meaning, and anybody in the States may know what does it mean, back of the envelope method. Basically, we needed to have a quick preliminary calculations for any deep excavation. Well, also we have to have a way to validate if we run some finite element analysis. We should have a reference, we should have a comparison. So usually the apparent earth pressure can provide us with a validation for and give us a quick check that we are doing right, doing really in the right direction. So this means that, okay, there is some development in this research, okay, that we will require to collect more data, more measurements, and with different stiffnesses, with different types of walls, different stiffnesses, and try to have an apparent earth pressure diagram and make it available for the profession. Conclusions, okay, pre-shearing of soil has explained the pattern of the jack-out pressure cell readings in the diaphragm wall. Measured apparent earth pressures goes along with the increase of diaphragm wall stiffness, having in mind that the stiffness that in the metro line the station was 1.2 meter thick, very very rigid. So because it's very stiff, so it measured higher, much higher pressure. The observed values are in agreement with many in the literature, and the current observations apply also to, yeah, this is something to say, because the sand that we have was dry sand. So maybe if we have wet sand or have a saturated sand, might not, but I think it will be similar. Uh, Again, we have to mainly think of the keynote over consolidated, keynote normally consolidated, if we are going to have a use of this normalized way of the apparent earth pressure. I'd like to thank my student, Sarah Ruweni. She is doing based on what we have. Okay, I directed her to start her research about the interaction of supporting walls for different types of retained soil in deep excavation, and she's doing her masters now. Okay, I have to acknowledge many people in Tanta University, Engineer Sarah, okay, Natural Tunnel Authority, okay, Engineer Nadia Abul Fadl. Yes, we run the monitoring. We uh, installed the instruments and we monitored ourselves, but we have their excuse and license to basically take it out and publish it out. And also I have to thank my colleagues in Hamza Associates, Muhammad Harfouch, Siham, Yasmin, Fairuz, and also I'd like to thank Techtrend Consult, the one who's really agent of the Geocon, who provided the instruments that we installed in the wall. Thank you. Any question? Huh?
Well, it's a discussion, but if you want to go back to the slide, can you put back the
slide?
go back to the trapezoidal three lines envelope and the red dots, which are the pressure cell readings. Yes. Berlin Wall. By the way, this is the future of the work in Nigeria. Nowadays, they don't go deeper than the water table. In Egypt, it's very common to go deep below the water. One more. But in the metro.
Yes, but in the metro, in the station, underground station, they go as deep as 40 meters. Yes. By K active or K not? Okay. Okay. Okay.
So look how smart was Peck, because you're saying they're underestimated the pressures. But if you look at the average, it's the envelope here. If you take the squares, the red squares, the middle one is higher, but the top and lower one is lower. So if you take the average of the curve, so if we draw a curve here, if we draw a curve here, and you take the surface area inside the curve, it's the same like the trapezoid. So the total push is the same. Imagine many years before we had pressure cell. It's very impressive. The overestimate, let's say that anchor fails, it will transfer, and I'm telling you this because of my experience, it happens, it will transfer to the other anchors and it will balance out. That's why you don't have many failures despite all the previous designs, because it's not correct, but it will become correct during execution. I like your comment.
Okay. First of all, you are implying that okay during the progress of the excavation there will be some changes and this will correct itself. But these pressures are the final after doing the excavation.
Because you have at the beginning, and then it goes up, and then it goes down.
Yes.
Remember, it's just a comment.
But you mentioned very important thing that what I can do is I can try what you mentioned is to have the area
Yes.
and then try to see if I mess or not. I'm sorry. It's just distributed all over the depth.
I'm trying to defend Peck.
No. Actually, I am very supportive to Peck.
Because I was with him in the picture. Remember?
Actually, I am his. I was his fellow. I got his fellowship. Okay, in UFI. So and I used to get lunch with him in every year to come.
Nice.
Yeah. So it was so nice to be with him.
And it's nice to be with you, man.
No, it's.
I really like your presentation because
you.
this
But
is
I
the
will-
future of
I will-
Nigeria. There isn't I think there's only one high-rise hotel with one basement below water, and it's
Yes.
giving them trouble. I don't want to mention the name, but I was consulting on that. But it is the future because the land here is becoming more expensive, and
Yes.
this came on time. Thank you.
Welcome.
Thank you. Yeah, I don't think there is any more contribution. Is there any contribution? Well, I hope the students. Thank you once again. Please a round of applause for him. Yeah, I hope you have taken a lot of notes from the keynote speakers, especially today's one that talks about excavation below the ground water table. Yes, I don't know if you have entered into some of underground or basement buildings where dampness is seriously disturbing them. Like the president said, I wouldn't want to mention. I think I was called to check one particular building in Abuja. Um, up to today, during the rainy season, the basement is always filled with water. The place that's meant to be a parking space, they won't be able to park any car there because even going there to inspect the site, I had to walk through water. So there's a lot of things to gain from this keynote. Please take note and you can ask questions. But if you can't ask publicly, please you can also meet Professor later, maybe during the tea break. So the next thing on our agenda is the tea break. So please, we'll go for the tea break now, and we'll come back here by 15 minutes past 10. Thank you. Yes. Okay, please, let's stay seated. Since we just resumed, let's have one or two technical presentation before we go for the tea break. Okay. So the first paper we have today, yes, paper 12. Yes, Sohad Said, a robust framework of Barcelona basic model parameter calibration based on conventional odometer test on Egyptian collapsible arid soil. Paper 12.
So,
Paper
big
12.
applause for Soha.
Yes.
The morning is controlled by the Egyptian delegation. It's okay.
Thank you. Okay, should I start now?
Yes. You have, sorry, you have, let me add 1 more minute to what I gave yesterday.
Oh, yeah. Point.
So you have 8 minutes for your presentation.
Okay.
Thank you.
Thank you so much. My name is Soha, and I'm here to present my study on a robust framework for Barcelona basic model parameter calibration based on odometer test in Egyptian soil. Please excuse my nerves because this is my first time, but I'm very passionate about my work, so I hope my passion overcomes my nervousness over time. And I also tried to change the color scheme of my work. It was like in blue, so I wanted to make it more with the theme of the conference, so I changed it because I like color coordination. I hope you know. Thank you. Okay. Okay. Before we start, my topic is on collapsible soil. And collapsible soil in general is unsaturated soil, and it has a very high strength in its natural state. But upon saturation, it overcomes radical particle rearrangement, which in turn also leads to settlement. Foundations on collapsible soil are relatively stable, as shown in this photo. But once saturation occurs, either from surface or subsurface wetting, they can cover from differential settlement, and that can cause cracks and severe tilting. Collapsible soils, the reason why I chose to study collapsible soils is because it's not a regional problem, it's a worldwide problem, and it covers vast areas all over the world. Specifically in Egypt, that's my hometown, that's where I'm from, and Egypt covers collapsible soil is very, very, in a lot of places, especially due to urbanization in the eastern and western deserts. The problem with modeling numerical modeling of unsaturated soil is you have to choose the accurate constitutive model. And I chose the Barcelona basic model, which is generally a continuation of the modified CAM-CLAY model, but it incorporates suction effects. And the problem, this is the problem, in that it's very difficult to determine the parameters of the Barcelona basic model because you need very, very sophisticated tests, especially suction controlled, and you need suction measurements. And once you do those expensive tests, either triaxial, you have to determine the data and you have to determine the parameters itself, which is a very difficult and tedious procedure. However, this research, it aims to promote the use of the Barcelona basic model in practical engineering. My aim is not only for research, I want practical engineers as well to also be able to use the Barcelona basic model so they can study the effect of collapsible soil and prevent failure. The main idea, I'm not going to go too in deep, and if anyone wants more information, I'm available afterwards. The main idea is since the tests for the collapsible soils are relatively very expensive, and some laboratories, they don't have the equipment, so we can't measure suction controlled, and we don't have the access for triaxial tests. So what the idea was that we can use traditional odometer tests that everyone has and everyone can access, and we can convert those odometer tests, which give us the data of vertical stress versus void ratio, and we can use very, very simple mathematical equations to convert the one-dimensional odometer tests, and we can convert them to the equivalent 3D isotropic stress state, which is how the BBM was formulated. So the whole idea is, since the BBM was formulated in a 3D isotropic state, so we need to find an equivalent so we can get the parameters. In my research, what I did was I took samples of some soil in Egypt, and we did some tests on the samples. This was the collapsible soil we used. And we performed single and double odometer tests on many samples so we could determine the collapse potential. And it turned out that this soil was in the medium collapsibility zone, so we had to study it and make sure that we knew the exact behavior and try to model it accurately. I'm not going to go too in detail of the equations, but this is the general formulation. The main idea is that I take the K-node line that I got from the one-dimensional odometer test, and I simply convert it to the normal compression line because that's all I need. To determine the parameters of the Barcelona basic model, basically all I need is a normal compression line. If I have the normal compression line of different tests, I can get all the parameters I need, and I can go into the software, and I can model the collapsible soil. From my test, I did many single and many double odometer collapse tests. I selected 4, and I determined the suction value from the soil water characteristic curve. Sorry. Afterwards, the first step I took was I took the data I obtained from the one-dimensional test, and using the framework that I previously mentioned, I was able to get the NCL lines for the 4 different tests. This is just some of the data. Okay, afterwards, once I prepared, so this was like the stage where I prepare my data so I can determine the parameters. So I used something called the sequential method. In the sequential method, it's based upon that I select the main parameters of the Barcelona basic model, and one by one I select it, but I don't put weight on a certain value. So when I do this, all I need to do the sequential method is I need 4 tests with different suction values. And that's what I did in the previous step. And I simply went through the sequential method and determined the main parameters of the BBM using mathematical equations and graphs. Afterward, I had my data. I had all my parameters for the Barcelona basic model. Once I had that, I could simply go into my software. I used Plaxis software to simulate the odometer test to make sure that the parameter estimation, so it was like a double step when I did the calibration. I was calibrating the framework to determine the parameters, and I was also calibrating the framework that I can use one-dimensional odometer test to get the 3D isotropic stress states without needing to do complicated triaxial tests with suction control. This is the result of my simulations using Plaxis 3D, and like I said, I used 4 tests. The 4 tests in these simulations, they were the same ones that I used in the parameter selection technique, but also because I wanted to make sure that my data wasn't limited only to the test that I used for my calibration in the beginning. So I also took 4 other random tests that were not included in my calibration methodology. I didn't use them when I was in my parameter selection or anything. They were just random tests. And I implemented them, and I did numerical simulation. And the results, as you can see, are relatively equal. I was able to model the measurements with the simulations. And in conclusion, my main target is that we can use the Barcelona basic model either in research or in engineering practice, and we don't need suction measurements. If it's available, it's okay. That's a plus. But if we don't have suction measurements and if we don't have the equipment to do triaxial tests, we can still accurately model unsaturated collapsible soil and get the behavior simply by using this framework. And we don't need soil water characteristic curves for the specific soil. If it's available, okay. If it's not, we can use in literature. So I hope you liked my presentation, and I hope I didn't take too long. Thank you so much for having me.
A round of applause for her. Yeah. A round of applause for her. Yeah, she has really done a wonderful research. You all know what is called the odometer test and triaxial test. Yeah, so trying to get triaxial results from odometer tests is a wonderful research, which I will employ most of Nigerian students here in all the 6 geopolitical zones to try to research just from odometer testing machine to get parameters, our C and 5 parameters. Definitely that would be a very big breakthrough to us. So please.
Thank you. Oh,
Thank you so for such an excellent presentation, excellent topic. I really liked it. I just have a question, not just to test you, but actually something that I really want to learn.
okay.
In your presentation, you were talking about Barcelona model as modeling the soil, the unsaturated soil, when it's get inundated with water.
Right.
When it's get inundated with water.
Yes.
Okay. However, my knowledge is that at a certain point, there are some occasions where may have the collapse with excessive vertical pressure, even if there is no water
Yes.
available.
Yeah.
So how successful is Barcelona model to model such case?
Okay. If I understand your question correctly, you want to know the effect of collapse without water. If the Barcelona or what exactly?
Yes, Barcelona model.
Okay. Barcelona model, it can accurately capture collapse either with water or without water. It's the main feature is that it. Okay. It can capture partially saturated soil behavior. So even if there's no inundation or there's no external source of water, it can still capture it because the soil will still it will be partially saturated. The main feature is that we can give as an input the suction value and we can input it into the soil water characteristic curve. So even if we only have vertical load and the vertical load will cause collapse, but the term collapse is in the Barcelona model or in collapsible soil in general, it's mainly accompanied with water. Yani, for forces, it's more like settlement, but collapse, it's mainly incorporated with water. But the Barcelona, from my limited experience, and I used it without incorporation of water, only with loads, and yeah, it was able to capture the effect in shallow foundations and in deep foundations. But all you need is to have the accurate suction value at the desired time. Did I answer your question?
Yes, okay. Thank you.
Thank you. More contributions?
Thank you, Sarah. Your topic is very interesting.
Thank you.
I would like to know how you did the stage construction on Placis for the odometer test.
Okay, I think, let me just clarify your question. You want to know how I did the stage construction for the odometer test, right? Okay,
Yes.
I used the soil test facility option in Plexus, but for the odometer, I had the actual test data, like I did the test in the lab, and then I had for each time step, I put the time step for each load, the incremental loading, and then I did incremental unloading and the saturation process, and I input all the exact times and all the exact loads into the soil facility option inside Plexus.
Okay. Hold on.
Sorry. I think that it will be better that you put it in your methodology so that people will understand it.
Okay, what he's saying is, yeah, it's just a suggestion about the procedure
Yeah.
of how the parameters, the odometer parameters were inputted. Of course, odometer parameters is not gotten in one day. So yeah, this is just the basic lessons for every geotechnical student to know how to conduct odometer tests and the parameters required for Plaxis. Thank you.
Question.
Of
Can you
course,
go
Mr.
back
President.
one slide back?
Okay.
I think with the limited time, you went too fast on this one.
Yeah.
And I want to understand because I cannot read clearly what's the green is Plexus simulation,
And the red is the
trying to
experimental
match the
results.
experimental one. This
Yeah.
way, we no longer need triaxial testing. We can hire Soha, right? Because she's matching perfectly.
Thank you.
Can you
And-
explain more, elaborate what you did here? Because you said we brought
Yeah.
samples from outside and you
Yeah.
tested.
We had a project in Egypt and we took samples from the project. We had like about, I think, 30 double collapse and single collapse tests. When I did the parameter selection framework, I used only 4 because the sequential method requires 4. I need 4 different suction values to determine the parameters of the Barcelona basic model. That's my first step, and that's how I did the calibration in the beginning. In the slide before that, that's how I did the calibration in the beginning. So these 4 different tests, they're the same test used in the parameter calibration technique. And then from the other odometer tests that I had, I didn't use their data in the parameter calibration. I didn't use it. All I had was the odometer test results, the experimental. So I took the suction value, because each one of them had different suction value. Sorry. Some of them were 5.7.
So you use Plaxis to predict.
I used Plaxis to
and
predict.
it matched.
Yeah, and match.
You
But
didn't cheat.
no, I didn't cheat. I have all my calculation notes if you want.
One more question.
Okay,
Why do
sure.
they call it Barcelona?
Because it was founded in Barcelona,
By
in Spain, by Alonso,
Eduardo,
Eduardo Alonso.
good friend.
Yeah.
Thank you, son.
Thank you so much.
A round of applause for her.
Thank you.
Yeah. Thank you, Soa Said.
Thank
Yeah,
you.
you can have your seat.
Thank you so much.
Thank you. Yes, the next paper is paper 13, titled Calibration of Monocolumn and Barcelona Basic Models for Partially Saturated Tropical Residual Soils. I think we have lots to do with Barcelona.
Okay, so thank you so much for the opportunity to present my work at this conference. So my presentation is somehow related to the last presenter, but just a little difference. I'm a Théobald Mézières. My topic has been called already. I'm doing a PhD student at Imperial College. So this is my presentation outline. I'll have the introduction, constitutive modeling of partially saturated soils, calibration of model parameters, outlook, and conclusion. Now, unsaturated soil is one of the hot topics in the world presently. And within the tropical region of the world, that is where we find unsaturated soil mostly because of the prevailing climatic conditions we have in this area. We can see the tropical region of the world, and Africa is largely in the tropical region, northern part of Brazil, southern part of North America, and some parts of Asia and Oceania. And then unsaturated soil within this region spans many depths, sometimes even up to 100 meters, because normally we have a very high rainy season within the period, and sometimes we also have another length of dry season, which accounts for this behavior. And what actually causes this soil to be partially saturated? Because when rain falls, a soil becomes saturated during precipitation. But actually, when the soil begins to dry, when sunshine comes, because of the amount of sunshine we have within the tropical regions, most of the water that have already gone into the soil gets evaporated. And because of that, we have a large change in suction, in flux balance within the soil. I believe all of us know the phase relationship in soil. We have the soil phase, water phase, and the soil phase for saturated soil. But when you come to saturated soil, we have the presence of A. This saturated soil, this is partially saturated soil. And then from the principle, which we already know, a very popular principle, we know that effective stress in soil is total stress minus pore water pressure. But for partially saturated soil, the principle does not hold because of the presence of A. And when the A is present within the soil with water, we have the kind of interface relationship between the two, what is actually cause the air-water interface, or also called contractile skin, acts like an elastic membrane which influences the mechanical behavior of the soil, thereby putting more strength to the soil. partially this affects this common the effect of partial saturation in common in tropical residual soil, collapsible soil, compacted fine grained soils. Typical behavior of soil under partial saturation, we have a suction in the soil varies with the degree of saturation. And this can be, this is the soil water retention curve. This is the relationship between the degree of saturation and the suction. As the degree of saturation increases in soil, suction reduces up to 0. So when the soil is saturated, the suction in the soil is actually 0, but at a very high dry rate, the suction is also very high. Then also increase in suction leads to increase in effective cohesion and pre-consolidation stresses. And this affects the strength of the soil. For instance, I made an illustration where I used the soil water retention curve to predict the shear strength in soil. You can see as the suction is, as the suction, as the degree of saturation increases up to 0, the secondary axis is the degree of saturation, while the primary axis is shear strength. You can see how we have shear strength, a very high shear strength when the soil has a low degree of saturation, but actually when the soil goes to dryness, suction also increases. But when the soil is saturated, suction decreases. Also, changes in suction induce elastic swelling or plastic collapse in soil, which influences the changes in the slope of normal compression. We're going to see this further in the presentation. Now, this is geotechnical infrastructures where the effect of partial saturation is common. We have the pavements, embankments, and shallow foundations. Considering modeling of partially saturated soils, this has been a process that has developed over the years, beginning with this more column follow criterion. You move to this expression by Bishop, which didn't actually capture the effect of partial saturated soil properly. Then from then we now move to the expression by Frelon and Morgenstern in 1977. And finally now we have the Lassoplastic model, which Barcelona basic model is one of them. And all these modifications that have taken place over the years are due to the evidences from experimental tests. Experimental tests still remain the most reliable information base for behavior of soils. Now, for hydromechanical modeling of partially saturated soils, this can be done in many softwares, numerical modeling software, for instance, Plasis. This is because the hydraulic state of the soil varies from time to time. That's what the hydromechanical modeling entails. Like, as the hydraulic state of the soil is varying, what is the effect of the shear strength of the soil? And then going forward, this is what I did here is actually a comparative calibration. So now, this is the Mohr-Column model. This is the extended Mohr-Column model based on the Frelon and Morgenstern expression. And then this is the Barcelona basic model. This is the principle upon which it was developed. And accurate modeling of hydromechanical behavior of soil actually depends on proper model calibration, which is now leading to what I did in the presentation. Now, going forward, first of all, I have the soil water retention curve. I did this with a soil test I obtained from, but I wasn't the one that obtained it, but it was already in the literature, so I used it to do the analysis. Now, this is the soil water retention curve of the soil. The red points are the measured points, while the blue points are the base fit. The base fit was done with a cell. We have the soil. You have two layers of the soil: the lateritic soil layer and the saprolitic soil layer. So the chair is somehow covering the other part of it. So this is first of all, I obtained the hydraulic behavior of the soil, and these are the model parameters. So why the fitting is actually done based on this equation, Van Genderen equation. And in the fitting, you are adjusting these model parameters within the limit of acceptable range. After this fitting, you can now be able to determine this model parameter, which in a way can tell you that, can be able to predict how suction changes in the soil during infiltration, during saturation. And then going further, we also have the hydraulic behavior, which is also depends on the Mohr expression. And in that case, because of the difficulty in measuring the unsaturated hydraulic conductivity, it is a common practice to use a relative probability to multiply saturated probability. So once you get the saturated probability from the soil, you multiply it by the relative probability, you can be able to get the unsaturated variation of unsaturated probability within the soil. Now, going further, these are the mechanical parameters because this, as I mentioned earlier, we are trying to do hydromechanical modeling. So we already have the hydraulic parameters. Now we have the mechanical parameters. For the molecular model, these are the simple parameters. But for Barcelona basic model, we have a lot more parameters. Now this is the flowchart for the calibration. First of all, you estimate model parameters for laboratory tests. After laboratory tests, you estimate your model parameters. There are a lot of equations for this. From that, we now proceed to define the model parameters in the soil model in the plassis. You define the soil parameters there. Then you define the initial conditions you used for the soil test. And then going forward, you run simulation and compare your experimental results with what you obtain from the plassis. If it is good, you can proceed. If it is not good, then you change the model parameters until. So once you have gotten the model parameters that match the experimental parameters, then you can proceed with your numerical modeling. And this is an example of a laboratory test. This was a laboratory test. This can be obtained from odometer concentration or from concentration stage in the triaxial test. This is for both for the lateritic soil and for the saprolithic soil. It was done at different suction, saturated 100 kPa and 300 kPa. And then this is the procedure that is used to obtain the slope of the normal compression line. This is by you fit from where the soil changes direction, which is called the pre-concentration stress. From that point, you can fit the points, find the first baseline, and from there you can be able to obtain the slope of the normal compression line for each of the soil. And then from that, moving ahead, you can also develop relationship between suction and pre-concentration stress. This was gives the loading collapse curve. To obtain this, you need to fit that equation above there, fit it within the suction points, and this is actually a very long process, which I may not be able to detail how it's done here. And then going forward now, this is the outcome of my calibration. After obtaining the model parameters, I simulated this in plassis, and this is what the Moore column gave, and this is also what the Barcelona basic model gave. And you can see, if you look at the two models, you can see that the Barcelona basic model is actually very, very good at predicting the behavior of the soil, especially the nonlinear behavior of the soil, as well as the increase in shear strength with suction. For instance, if you look at the Moore column model, when the soil is saturated, it was able to, it tried in predicting the ultimate strength of the soil. But once the soil contains some suction, it wasn't that good again. But for BBM, although there are some points where it's underpredicted, which could be due to variability in the laboratory test, but overall, it gives a good trend when compared to the Barcelona basic model. And then also for the saprolithic soil, the same trend was also observed. You can look at how the prediction was done for BBM and then for prediction for Moore column model. Then, okay, these are the final model parameters for this. For each of these are the model parameters that actually gave me the prediction that I showed in the previous slide. And then outlook, my next plan is, because I'm trying to make this as practical as possible, I'm going to construct a model in which, just like an embankment model, in which I'm going to use both the Moore column model parameters and BBM Barcelona basic model parameters for both of them, and then apply them for which I'm going to allow them to fall for a particular time, allow it to dry, then allow it to rain to fall again, and then see how this will affect the behavior of the soil. I hope I could have opportunity to present the outcome of this in the future. And then finally, the conclusion, there is evidence that VBM definitely perform better than MC in modeling the nonlinear behavior of soil, as well as increase in strength due to suction variation. It is expected that BBM is incorporated and utilized in routine geotechnical engineering designs for safe and economic designs, especially in the tropical regions where soils exist in state of partial saturation most times of the year. I'm looking forward applying this in real analysis to examine the performance through real numerical model analysis. And finally, the key challenge could be how to integrate this model into design codes and standards. And this is a research that we young engineers can pioneer. Thank you so much.
A round of applause for him. This is also another wonderful model and experimental research. Yes, it's very difficult to add both together in one research. Yes, and I have a question myself. Yes, your model graphs. So this BBM, the model equation is not written by you. You only adapted what. Yes.
Yeah, yes, of course.
So is it possible to twitch this equation? Maybe look at the the parameters and see those ones that may fine tune your own research so that it can be more adaptable. Thank you.
Okay. Sorry. Yeah, thank you so much for the presentation. Personal basic model actually there has been a lot of developments over the years for it. For instance, it was developed by, just as you mentioned, developed by Alonso et al. And then there are also some other developments, but the behavior of the soil varies from place to place. Maybe the soil, it was the soil upon which it was used to develop the model may actually give a good prediction, but when you come to a different soil, may actually have another different behavior. So it is something that is possible. It can be done, but I think it's something that also requires a lot of work to do that. So if I don't know, it's not within the scope of my research, but if something I can do in the future, I will actually have to do that, especially for lateritic soils. Yeah, thank you so much. Yeah.
Thank you.
Excellent presentation. I'm interested in your two types of soil, lateritic soil and the saprolite. What actually are the basic differences? That's one. And in answering it, the applicability, just like the last question I mentioned, lateritic soil is something else that has a lot of challenges. Does this Barcelona basic model actually capture the peculiarities of lateritic soil? Because I saw the parameters, these are parameters you came up with. Are those parameters actually applicable to laterites the way they are, the way we know them to be?
Thank you so much. Okay, so for the first question, the soils we are collected from in Brazil. We have the soil were collected by digging through the soil. So within the first 2 meters is lateritic soils. Then below that we have saprolitic soils. They actually have little differences. From the literature itself, the lateritic soil, the predominant minerals there are hematite, gibbsite or so. But when going down, we have soil that contains more fine, based on what was reported in the literature I used for this. So there is different, just the subsoil, different subsoil within the area. And then regarding the second question, there are some behavior observed in lateritic soil, like collapse upon wetting, which is typical for which is also what Barcelona basic model can be able to capture. But soils, just as the previous presenter showed, the information about collapsible soil, which Barcelona basic model, which laterites also have similar behavior. So based on there's also some literature that was really reported that this model has capacity to capture the behavior of lateritic soils, especially collapse upon wetting, but there is still room for improvement, and there has been other improvements that have been done, which I may not be able to summarize all of them here. But there are some researches from Brazil where this has also been used to show that it is possible to simulate the behavior of lateritic soil. Thank you so much.
Thank you. Thank you. Yeah, Nigerian students, this challenge is over to you. Hopefully, in the next AYGEC, we are expecting NBM model, Nigeria Basic Model. Please work hard. Thank you. Yeah. Okay.
Okay. Thank you very much. Your topic is very interesting and clean. Your topic is very interesting. I really love it. Yes. I have some question for you. The first question, for the retention curve, which software do you use to determine the parameters?
Which one? So, software retention curve.
Yes.
Yeah, I use the sales server. Sales server is a optimization tool. So it's basically you can obtain the model parameter by optimizing the error, optimizing the error between the measured values and the predicted values. So yeah, it's fun. But you can also use something like MATLAB or even develop a Python equation to do that.
Okay, thank you. Another question. The design.
Yeah.
Can you go to the slide where you show the design?
Oh, sorry.
Yes.
Is it this? Okay. Yeah.
Yes.
Yeah.
You have an impermeable boundary.
Yeah.
After that, you have a saprolic soil and lateritic soil, and under you have a slope, something like slope, and a load.
Yeah.
I would like to know if for your design, you will take in account the effect of the load and also the effect of the rain. Because in this case, I think the problem is more in the transportation of water in the soil. So not only the load problem. So I want to know if you will do this
Okay, I think I got your question.
In French, we call it analyse couplée.
Yeah.
Okay.
Okay. My plan is to simulate exactly what happens in the environment. For instance, we already have the subsoil comprising of lateritic soil and saprolitic soil, right? And if you are trying to build a road, you construct an embankment, right? For some places, not all places, but most cases, you raise the line. So I'm going to simulate construction of embankment where I will construct the embankment in 4 layers, and each layer is maximum of 250 millimeter, right? So that is 4 layers, 250 millimeter, that's total of 1 meter. That's the height of the embankment. Then after constructing the embankment, I'm going to also construct a vehicle load, right? Which is span about. I'm doing this in half symmetry. It's possible to do analysis in practice in half symmetry to reduce the analytical resources, right? So I will do it in half symmetry, and you know that the typical road have a width of 7.3 meters. So I just use half of it, which is 3.65 meters. And then after constructing the road, I'm going to apply a vehicle load on it, which is what I represent there by the arrow that is pointing down. Then after that, I'm going to now apply rainfall. For instance, if after building a road, rain falls, and for some time rain falls, and then it gets dried up again, what will actually happen within the soil? How will the column model predict the displacements, a factor of safety of the slope, and how will personal basic model predict that? So that can give us a good idea of how which of the models can actually be a good model at getting the behavior of the soil. Yeah, thank you.
Thank you. Yeah, so the breakfast is ready. Please let us go and have our breakfast. Then we quickly return to continue the technical presentation. Thank you, everybody. Sorry, tea break. Tea break.
to love me. Doro me, baby. Doro me, Doro. Kilo de, oh.